In this video, we're going to look at how a linear search works. A linear search is one of the easiest algorithms to implement in terms of searches. There are many out there. We're also going to look later at a binary search. A linear search will work. It will eventually get there. However, it's pretty slow in a lot of cases. The only time linear search is good is if the element or the item you want is at the very start of the list or the array. If it's at the end, it's particularly slow. An example would be if I, in the school database, want to search for somebody who had a surname with Z, it's probably going to have to go through 2,000 different students to find that person with the surname of Z. It takes a long time. However, if the first person's surname was Atkinson, with an A there, it's going to be a bit closer at the start. So, although linear search is incredibly easy to write in code or write in pseudocode, they're not so useful in computing. They're not used a lot. However, it's useful to know how it works and to see how this really simple algorithm was thought about. This time, what we'll do is we'll treat the list or the array more like a computer sees it. So a little bit like it's on the screen at the moment. The actual computer doesn't actually see the full list or the full array at once. All it sees is that there is a list or an array and it has so many items. We could say like maths X number of items. In this case, we can see it's got 6 items that fit from index position 0 to index position 5. So what happens is it starts at the very left item, so position 0, and it says, is this the card I'm looking for? So with the demonstration here, I'm looking for a card with a value 7. So what it does is it starts at 0 because it says, okay, is this the card I'm looking for? If it is the card I'm looking for, then I can stop exactly where I'm up to. Okay, so here's an example. First card, is that the number 7? No, it's not. So I go on to the next item in the list. Okay, is this card the number 7? No, it's not. It's a number 3. Is this card the number 7? No, it's not. So it keeps going and increasing it the count of 1 at a time to find the right item. Nope. Is this the card I'm looking for? No, that's a 2. Is this the card I'm looking for? Yes, that is a 7. Okay, so we can see in that case we've had to do that same instruction or selection statement once, twice, 3, 4, 5 times to find item. In fact, a linear search would not even be able to find the item at all if it wasn't in the list. And that can be a little bit of a worry as well. Actually, it's not even in the list and we're going to do a search for it, which is a bit inefficient because in this case, we could search through the whole array and not find the item we wanted to. There are better ways and quicker ways of doing that with very large items or what's called big data in computing. So I want you to have a go at doing this, but this time slightly differently. I want you to think about, is this efficient? What's the best case of a set of 6 cards? What's the worst case scenario for the algorithm if it's got a set of 6 cards? How would that work if it had 1,000 items or 2,000 items in there? It's just a good way of doing it. So the positives of using a linear search is it's really easy to implement, but it is very slow and it is very inefficient. So there are better ways, but it's a good way of knowing if you think about programming and you don't know any other way, implementing a linear search always works and finds what you want if it is in the list, but it is quite slow. So you're going to have a go at doing the same thing with your cards, and then you're going to try and write an algorithm or a set of steps, ordered steps, to try and write down what somebody would have to do in order to perform the same task that a computer does using a linear search.